Hello, this is a very quick little video because I've been programming or vibe coding for way too long and I should go to sleep, but I'm way too interested in this. So today we got our little FPGAs connected to the internet and I'm having time of my life with it. I should probably go outside. I made a little SDK, like a Python SDK, just allows for a little bit of a better interface here, and it's inspired by modal. And the idea here is that we have some FPGAs, right? These are the reconfigurable silicon chips that we want to access, and the reason we want to access them is because we want to design computing hardware, right? The digital circuits that enable your computer to work, and we want to design these remotely here, and then we want to just be able to program them in actual physical silicon on this FPGA somewhere. But this is so insanely awesome because it's so simple. So here we have Andrew's SAT solver he built. It's a brute force SAT solver that is implemented in hardware that's going to be run physically on a silicon chip on our FPGA at Barnard 9th floor. In here we just have a really simple interface to play with it, and it's so great. So we can define our register map. If you're not familiar with hardware stuff, the way it works is we'll talk to some peripheral, right, on some sort of system, and the way you typically talk to it is you'll just read and write to it as if it was like as if it were like a file of some sort, right? So we can read it and write to specific addresses in the same way we read and write to memory, and then this peripheral can then also read and write to those same addresses, and that allows them to communicate back and forth. So this is really cool because we can define this register class. Or to start, let's take it a step back, right? We can import our cloud FPGA package here, and then we can use that to define a register class where we can define the actual register map we want to use, right? These addresses which we're going to allow to communicate between the peripheral and the host. So we have a control address, the number of variables for our SAT CNF, whatever you want to call it, the number of clauses in our CNF. The hell do I even know what the fuck a model is? I vibe coded this, I don't know. Something important, I guess. Valid when SAT equals 1. So that's model check. Who knows? Cycles, which are maybe that's a limit. Who knows? But the great thing is we can communicate back and forth with a peripheral and a host, and that's really cool. And it's all abstracted there for us. Going a little bit down, we have, let's see here, I haven't even read all this. We have a byte address of a literal register. So this seems to communicate, what is this, in the word where our literal and our clauses and whatnot, something like that. And then encoding this is all just fancy schmancy SAT stuff that we don't really care about. The real beauty and meat of everything, the real meaty part of this here is this modal inspired app here where we can fill these parameters so we can apply our design here. So this is our SAT solver design. We're going to, I'm saying a lot, this is our FPGA ID. Right now we only have 0 and 1, so 1 and 2, right? And these are our registers that we're loading from our register class. And this is our API key, which is just like a bullshit API key because it's not authenticated at all, and that's a big issue right now. But that's there. And then this signifies our entry point to actually play with our FPGA. So the really cool thing here is that traditionally when you're dealing with these FPGAs, you have to deal with these really low level writing in C and whatnot, where you're actually writing device drivers and whatnot to communicate with some peripheral, and it's a major pain in the ass if you've done it before. So the fact that here's as simple as running a Python script and you're communicating with a hardware device somewhere is really insane and really awesome. And yeah, we can see here we're defining our clauses for our SAT problem, number of variables, number of clauses, and then we just call .write for our app, and we just write to our register map. The variables, the number of variables, number of clauses. We can write our actual literals that are getting encoded, and you can see that there as to where they're getting written. getting written somewhere, huh? How the hell? Oh, here, address. We write to register map here. We print a little solving. We do a little solve, and then we can read it, which I guess is what Cycles is doing there. I don't know. And we can print it out, and this is really cool. We can also access our CLI, so we can see what FPGAs are available and whatnot, and they're all idle. And then we'll actually just straight up and go do this. So we can do cloud FPGA run, and we're now programming it. So if we check it again, we're now in the building mode. It's beautiful, and we'll have to wait like 300 years for this to load, but we'll give it a second. Alright, so it looks like we just finished, and beautiful. We're seeing the print solving, and you can see exactly we got SAT. And the beautiful thing about this, right, and why we're so focused on SAT solving is the idea that we can do reinforcement learning with verifiable rewards, because here we just got a verifiable reward signal. We can actually just look through this. Oh, so that's what the model is. It's actual SAT formula, I guess. We can actually read through this and identify if this satisfies it or not, right? So it looks like we have, what is this? 2 clauses, and we can look and see if this actually satisfies it. So say x1 is false, x2 is true, x1 is false makes this one true, and x3 is false. And yes, that's correct. This satisfies this. So we just did that in polynomial time, and that's really insanely cool. And we can actually see here too, if we check the status again, it's in reserved now, and the owner is me, dev. And this is insanely fucking awesome, and you should give me $1 million. And yeah, that's really about it. I'm in love with this. This is so cool.